Okay, I'd like to talk about what an algorithm is. So, the key idea of all of programming, and especially of this class, is an algorithm. So technically speaking, an algorithm is a finite sequence of precise steps to solve a problem. So the first thing to notice is that it's steps to solve a problem, so you get an algorithm to solve certain things. Algorithms can be written down in a lot of different ways. Computer programs are algorithms, but so are a bunch of other stuff. And notice that it's a sequence of precise steps. So every step has to be specific enough that you know how to do it. And it's a sequence of them, so the order of an algorithm is always important, or almost always important. If you mix the steps up, it won't go in the right order. And that's what a program essentially is. It's telling the computer what steps it needs to go through to do something. But you can have algorithms which aren't programs. So what I usually do right here at the beginning of the semester is we talk a little bit about algorithms in general, and then we move on, of course, to do computer algorithms, programs in just the next week or so. Okay, so first of all, for this lecture, I usually just show a bunch of quick examples of algorithms which are not programs. Here's one on the left. It's the how to assemble an IKEA Billy bookshelf. So if you look at what they've got here, they have some pictures, and then down here they have the steps. Step 1, identify the parts, start the assembly. And they have pictures to help, and they actually list the parts here, 1 back panel, 2 side panels, and so on. And 2, start the assembly. And they say insert the 6 of the wood plugs into the side panel holes with your thumb. Then it tells you a little bit more. And then carefully push the bottom flashing, bottom shelf, and top shelf onto the plugs as shown in the photo. That's actually several steps, right? So really this algorithm has already got a smaller algorithm inside it, which is a whole series of smaller steps for starting the assembly. And then step 2 is the second side panel. Again, they have pictures, and they tell you push the remaining 6 wood plugs into the remaining side panel, then carefully place the side panel on top of the others, line them up. So again, we've really got, in this step, we really have a whole series of smaller steps. I'll attach the left side panel with screws, and they have stuff for that. And step 4, screw together the right side panel, and so on. So this is an example of an algorithm. It's just like any other algorithm. It has all the same kinds of elements. It's got a sequence of steps. Each step is precisely specified enough that hopefully you know what to do. They're hoping that even if you don't know exactly what you're doing yourself, you can do everything they tell you. You can push things in, you can do all the rest of it. They don't give you an algorithm for the things that are obvious, like they don't tell you how to carefully push the bottom flashing. They assume as a human being you know how to push things. They don't tell you how to align things together. They assume you know how to do that. Even there, they show you pictures. Notice that one of the first things you do in this particular algorithm is to assemble all the pieces you're going to need. And that's really typical for a lot of algorithms. A lot of times it's helpful if you first assemble all the sort of the raw materials that you have. And I'm going to pay close attention to that later. I'm going to compare that to variables in programs because there is sort of a connection. There's at least it's a good analogy. So here you start by collecting all the different pieces, and then you do things with them afterwards. Notice that each one of these steps is actually made up of a smaller algorithm, which is all the steps for doing that step. That's typical also, and there's something sort of analogous to that with programs. In programs, you often have what are called subprograms, which are smaller programs that become one step of the bigger program. And so sort of keep that in mind. Okay, that's the first example. Here's another example. This is how to do the floss dance. So 1, mastering the move. A, stand with your feet shoulder width apart, hands twisted at your sides, face the front of the room and square your shoulders. And a little tip that keep your knees slightly bent. 2, sweep your arms to the left, and they have a picture for that. And keep your arms straight and your hands twisted as you do this, and so on. 3, push your hips to the right, we'll swing your arms up to the left, and they have more details. They can think of your arms as forming a 45-degree angle with your shoulders. Your hips should only move side to side, don't push them forwards or backwards. Put your hips out as far as you like. The closer you keep them to the center, the faster you can go, but the more you push them out, the more dramatic it is, and so on. And 4, and 5, and 6, and so on, 7, and that's method 1. So once again, you have a sequence of precise steps. Notice how precise the steps get. You have to be able to do the steps without any further explanation, or the algorithm isn't specific enough. So, like down here, they actually get very, very specific. Your hands can come out to about halfway between the side of your body and shoulder height. Your hips should only move side to side, and so on. Notice that for both of these, because it can be, well, let me just point out, with every algorithm, it turns out that it's really difficult to specify algorithms so precisely that people can follow them. It's very easy for them to get mixed up. So in both of these, they've had pictures to help. That's not a coincidence. It's because it's hard to clarify what an algorithm should look like. So here they've got pictures to help, and the other one they have pictures to help. Notice that you have choices within an algorithm if you want. Like here, it talks about the fact that you have your choice about how far to push your hips out, because closer means you can go faster, but farther out means it's more dramatic. So just because something is precise doesn't mean you can't leave choices up to the person following the instructions. In the same way, computer programs will have choices too. They'll say, they'll ask the user to input something, and if they input this, we'll do it this way. If they input that, we'll do it that way. Precise doesn't mean limited. You can have all sorts of different options within a program as long as it's clear what option to pick. As long as you know what the option, how to know, as long as the program knows what option has been picked, as long as there's a way to distinguish between one case and another. So anyway, that's another example of an algorithm. Here's a third one. This is a typical algorithm. Recipes are algorithms. Recipes start with a list of ingredients, 18 egg whites, 2 tablespoons, etc. And then below that they have the directions, which is where the algorithm proper occurs. Preheat oven to 350 degrees, sift cake flour and confectioner's sugar together 5 times and set aside. In a large clean bowl, whip egg whites and so on. Quickly fold in the flour mixture, etc. Notice that some things, again, sometimes they have a big step, like number 2 here, that actually involves several small steps inside it. Notice that they're assuming that you can follow the things they tell you. One of the things that's true for every algorithm, again, is that they're making certain assumptions about what you're able to do and not able to do. And the steps have to be precise enough that you're able to do whatever they ask you without further instructions. Otherwise, your algorithm isn't really complete. Notice that sometimes you have a choice about how long to do something. Gradually add sugar while beating and continue to beat until very stiff. So you just keep doing it. How long? Well, however long it takes for the egg whites to get stiff. And that's when you are done with that, and so on. So in the same way, a computer program often has a loop that goes on until some process is finished. Keep doing this until the user says they're done, or keep doing this until you've done it 20 times, or whatever else. Notice the ingredients. This is sort of like the list of materials that you looked at in the IKEA how-to. A lot of times algorithms are easier if you first start by pulling out what materials you're going to use, and then you look further to see what you're going to do with them. We'll talk more about that in the next video. Here's another set of instructions. This is part of filling out a tax form. So you'll notice this particular section on page 20 is figuring out who qualifies as dependents. So step 1 is to decide if you have a qualifying child, and it has several different options of how you know you have a qualifying child. Step 2, are they your dependent? And it gives you several different ways to determine if they're your dependent. Was the child married? Yes or no? Was the child a citizen? Yes or no? And so on. Does your qualifying child qualify you for the child tax credit or other departments? So check this, check that. So this has a series of steps. The thing I want to point out here is there are a series of questions within these steps. So if this is true, do this, but if that's true, do that. So it asks, is the such and such the case? If yes, do this. If no, do that. Was the child married? Yes, then see married person later. No, continue. This kind of thing happens in programs all the time. You ask a question, and depending on the answer to the question, you either jump to some other part of the program and do things there, or you stay where you are in the program and do other things here. That kind of thing will happen all the time in flowcharts and in pseudocode. So it's a very typical thing. Again, that means that a sequence of steps for solving something doesn't have to mean that there's only one option. It just means that if you have several options, you have to be precise about all of them, and you have to be precise about how to know which option to follow. You have to be able to get an answer from the person. Was the child married? Okay, let me just give you a couple more examples. This is an example that we looked at the other day. This was our sample program for CIS 150. Certainly programs are algorithms. They're not the only kind of algorithm, but they certainly are at least the expression of an algorithm. So this algorithm starts by saying, sort of like an ingredient section, we've got an I and a j and a sum to hold on to our values. And then it says, output, enter 2 integers on the screen, and then whatever they type in, put them into I and j, and then add I and j together and put it into sum. And then output I and a plus and j and an equals and sum and a new line, and then return 0 and stop. So this is an algorithm for outputting the sum of two integers on the screen. And it's got different steps, and the computer has to know how to do each of these individual steps. It has to know how to do the output, and it has to know how to do the input, and it has to know how to do the addition. Notice again that there's so one of the things we're going to hit later on is that every single time there's certain things you assume you already have available, like ingredients, so to speak, and there's also certain operations you don't have to explain. Like you do not have to write a program to tell the computer how to add. That's because that's built into the chip. Every computer chip has the ability to add two numbers in it. It's actually built in. Now somebody somewhere when they wrote the program, the chip had to have like a smaller algorithm for adding numbers, and that's built into the add operation in the chip itself, in the circuitry. But we don't have to worry about that as programmers because that's already built in. And then finally, here's an example of a flowchart. I don't know how clearly you can see this. This is available in Canvas. If you go look under the modules, you can find this example and open it up and look at it yourself. This is using, I think this fits exactly our rules for flowcharts in this class. So this would be a legitimate answer in our class if you ask for something. What this does is it's a silly little program that figures out the amount of pennies, quarters, nickels, and dimes that you need to provide change for something. So you'll notice that we start with the block that says start on the upper left, and we follow the arrows. So the first thing you do is output the words enter the price $1 or less. This NL means new line. It means we then move to the next line. So this will actually put on the screen the words enter the price $1 or less. Input the price simply means that whatever they type in, if they type in like 73 cents, it will put into the variable price. Now, how do we know there's a variable? Well, over here's our variable list. This variable list right here is like the ingredients list. It's like assembling all the materials beforehand. And what we've got is 5 different variables: price, quarters, dimes, nickels, and pennies. Think of each of those variables as being a box which can hold values. So this price is a box, and we're putting into it whatever the user typed. So if the user typed 73, actually we're assuming the user types like 0.73, 0.73, we'll call that, we'll put that into price. Now it checks whether the price is greater than 1. If they typed in 0.73, they've got something less than $1, then the answer is no, so it'll move on this way. If they typed in, say, 1.73, $1.73, we go to yes, B, which jumps us over to here where the other B is and moves down and says this program cannot handle amounts over $1 and stops. That is, you follow this arrow down to here and keep following this arrow over to here, and it stops. So this program, if you give it an amount of $1 or more, it just bails out, or more than $1, it just bails out and says, I can't do that. Otherwise, it puts 0 into the quarters, 0 into the dimes, 0 into the nickels box, and then puts into pennies the price times 100. So if the price was 0.73, it would put into the pennies 73. We move down to A, which brings us to A over here, come to here. 73, we ask if it's less than 25. If the answer is yes, we follow the yes branch, and if it's no, we follow the no branch. So 73 is not less than 25, so we follow the no branch. We add quarters gets quarters plus 1, or quarters equals quarters plus 1. What that does is it takes whatever used to be in quarters and adds 1 to it. So quarters used to have a 0 in it, now it has a 1 in it. And then this pennies equals pennies minus 25, or it's often read pennies gets pennies minus 25. Pennies used to have a 73 in it, now it has a 48 in it. And then we follow this arrow, which takes us right back around and cycles us right back to where we were. It asks if that 48 is less than 25. It's still not. So quarters gets 1 more. It used to have a 1 in it, now has a 2 in it. And pennies used to have a 48 in it. It now has a 23 in it. And then we cycle back around and ask if that's less than 25, and it is, so we come down to here. We have to ask if pennies is less than 10, and it isn't, so we move to the right. Dimes used to have a 0 in it, now it has a 1 in it. And pennies used to have 23, now it has 13. Come back around, that's still not less than 10, so we follow the no branch. Dimes used to have a 1, now it has a 2. Pennies used to have 13, now it has a 3. So we cycle back around and ask if 3 is less than 10. It is, so we follow the yes branch and come down here. And ask if 3 is less than 5. Now if it wasn't, we come down around here and add to the nickels. But it is less than 5, so we move down here, leave nickels set at 0, which it already was. We output quarters, which at this point was 2, and then the word quarters, and then a new line. And then we output dimes, which was 2, and then the word dimes, and then go to the next line. And then we output nickels, which was 0, and the word nickels, and go to the next line. And then we output pennies, which is 3, and then the word pennies, then go to the next line, and then we stop. So this is an example of a sort of a silly little flowchart. This is the kind of thing you'll be producing. in flowcharts, there's all these different shapes, and there's a different meaning to each shape, and we'll talk about the shapes you can use. But the main thing is you start at start and end at stop, and you run right through the list. Whenever you see one of these diamonds, you have a couple of options. But the thing in the diamond is completely unambiguous. It's easy to tell whether pennies is less than 25 or not. Either the answer is yes or it's no. It's easy to tell what to do in every single situation, and we use the price and the quarters and so on as we go. All right, I'm going to build on this in the next video and set you up for the first assignment. But that's the basis of algorithms. One of the things to notice is, well, no, I'll leave that alone. I'll talk about some of it in the next video. Thanks.